total. And also going to talk about that sort of fundamental problem connected with counting, but now introducing privacy as well.
Thanks. Thanks to the organizers for inviting me. Thanks to Jelani for actually giving the main message of this talk as well. Basically, there's a saying in French, which is, I think, translates roughly as it's in the old pots that you make the best soups. So the same way that there was an algorithm that was actually optimal and we didn't know it, there's going to be a similar story here. So I want to say this is joint work with Abigail, who's somewhere in the audience. So all the mistakes are mine, but if you have any interesting questions or comments, that should go to her. So I'm going to talk about locally private histograms in all privacy regimes. I'm going to try to convince you that this title makes sense. That's the usual thing. So I'm going to start with what I mean by the distributed setting and the problem itself. So, OK, typical story, users have data. I'm going to think of that as observations. And there's a center somewhere that wants to collect that data and learn from it. For example, I guess a lot of you flew recently. I might ask, which airline did you take? Or what kind of meal did you have, et cetera, just to get some statistics that I can use to do some data science. So this data very often is personal. You might not want to know people to know which airline you took, whether you asked for a vegetarian meal on the flight, and so on. So I'm not going to. Another version would be the observations I ID from some underlying probability distribution. I want to learn something about that distribution. I'm not going to talk too much about that. I'm going to talk about the first one. There's a reduction between the two. And the question is that I want to learn about the user's preferences. So each user has one piece of data that lives in a giant universe. I'm going to call that size k. Think of k as being really large. And I want to learn the histogram. So how many people took United Airlines? How many people took Qantas? If you know what that is, that's the one I took. And you might not want to reveal that too much. So again, users have data, observations, so n users, n pieces of data distributed there. Each person has one piece of data. And users have constraints, typically here, privacy. You might also want to think about bandwidth. You don't want to communicate too much. It's a distributed setting. But the main one is you don't want the center to learn too much about your personal kind of data. And the center has its own goals, meaning it wants to actually learn something useful. So you could think of that as I want to minimize the number of users to achieve an accuracy target. But here, given the fact that I've got a bunch of users, and I want to maximize the utility I get. So I want to learn as well as possible, given the number of users that I have in the room. How many of you are familiar with differential privacy? OK, so I'm not going to ask on the internet. But yeah, so typically you have many more than that, but several variants of differential privacy, depending on who you trust with your data. So the typical one, the one we think about most often, is the central privacy. I trust the algorithm. Everybody gives their data, and the algorithm does something, and the output should be private. Local privacy is more I trust nobody. My personal data should not leave my phone in the clear. And there's something in the middle, shuffle privacy, that I'm not going to talk too much about it, but it's intermediate, and that's actually one of the motivations for looking at the parameter regime I'm talking about. But I'm going to focus on local privacy, where really you don't trust the algorithm, you don't trust anybody. You don't want anyone to learn really for sure what your data is. And the obligatory slide, but in my own writing, this is the definition of privacy tailored to local privacy. So a user has their personal data and is going to send a message to the center. R stands for randomizer. And the idea is if I had a completely different piece of data, so maybe I have X, but if I had X prime, the distribution of my outputs, the probability distribution of what my message could be, should be roughly the same. What does roughly mean? Should not differ by each probability of the probability of each message should not change by too much a factor. E to the epsilon. Epsilon is my privacy parameter. So if you check epsilon is equal to 0, all the messages have the same probability, all the messages have the same probability, and I give 0 information. And if you're wondering why e to the epsilon, well, e to the epsilon is roughly 1 plus epsilon. So the joke is epsilon is equal to 0.1. E to the 0.1 is roughly 1.1. Epsilon is 10. It's roughly 11. The problem we're going to look at is histograms. It's also called frequency estimation. It's related to heavy hitters. It has been studied extensively in a lot of settings, streaming, local privacy, central privacy, like a lot of things. You want to learn that beautiful thing, basically. So I want to learn how many people took United, how many people took Qantas, how many people took Air France, I don't know. And I want to have good error simultaneously on all the bins. So I've got n data points. There, each person has one. They're private. They belong in a universe of size k. K is large. I want to learn basically the empirical frequencies of all of those. And I want to minimize my L infinity error, which is the maximum error on all those bins. And there's an expectation here. The expectation is over the protocol's randomness, because I'm going to randomize. Each user is going to randomize their message to ensure privacy. So there's going to be some error. If I didn't have privacy, I could very easily have error 0. So I hope the goal is clear. I want to learn the histogram such that my expected L infinity error is small. So that's histograms. I said it has been studied, and like it has been studied extensively. We know the answer. Here's the optimal bound up to constant factors. The best achievable error is theta of square root log k over n epsilon squared. It is known. The dependence on the domain size is actually sublinear, so that fits really well. The dependence on the privacy parameter is epsilon squared. So you can check that when epsilon is equal to 0, you learn nothing. And what's even better is like this is achieved by several protocols, including very efficient ones, including some with very little communication per user, like essentially log k bits. Log k plus 2, I think, is the actual thing. So, you know, we've got something that's private, optimal up to constant, and efficient in all possible regards, so we're done.
Sorry, so K is what?
K is the number of airlines.
Okay,
Yeah.
N is the number of users.
N number of users, yeah. So as n, if n is really large, you have smaller error. If k is really large, you have bigger error. So at this point, it looks like we're basically done. The catch is all that is for small epsilon, which is also the high privacy regime. It requires a little bit of mental gymnastic. High privacy, low epsilon. Low privacy, high epsilon. So, okay, but you know, that's still good. The question is, what happens when epsilon is large? Again, think of epsilon being like 1, 2, 3, up to log k maybe. Then it's really not quite known what the answer should be. And I would like to argue that's also a setting we should actually care about, even though that doesn't provide a lot of privacy on its face. So to take a step back, what do we want and what do we need? Well, we want simple and efficient protocols, something that can actually be implemented in practice that fits well with the theme of this workshop. Low communication, that's related to the first one. I mean, I'm not going to give that. Something non-interactive, by that I mean you don't really want to enforce the users to have to like have a full dialogue with the center in order to communicate, because those things are really hard to implement. And you know, if it's on your phone, you're not going to wait for your phone to have like 70 rounds of interaction with the server in order to finish. Same thing, you don't really want to use public randomness. So there are like a lot of very cool techniques allowing you to do a lot of things if all the users share a common random seed. But again, that might not be the simplest to implement. If you can, that's great. If you can't, then that's most of the settings I can think of. And you want good error, including in the low privacy regime. I think this is really important. Why is that? This, okay, I even have a reference. This is coming from the Apple differential privacy overview. The highlighting is by me, it's just the epsilons they use. And each of them, like, if you do that several times a day, you have to multiply that. So, you know, epsilon is 4, 8, 2, 4, 8. You know, typically the range where like e to the epsilon is not exactly the 1 plus epsilon you would think of, but also the range where like the guarantees you would get from the previous papers are kind of vacuous, and also the lower bounds do not apply, sorry. So, okay, I'm gonna give a detour. Jelani talked about sub-gamma random variables. I'm gonna talk about sub-Gaussian random variables. If you haven't seen that, you can, this is a very cool math fact. This is not very extroverted, but that's something I think everybody should know. If I've got a bunch of sub-Gaussian random variables, think of Gaussian random variables, and I want to take the maximum, they don't need to be independent. The expected maximum grows as square root log k, if I've got k of them. That's a very, very neat fact. It's been used, it's not new. It's well known by everybody who knows it. I'm gonna cheat a little bit, but there's a simple thing. If you remove the absolute values, here's the proof. Basically, like it's a 4-line proof. It's kind of a classic trick. It's really neat. I'm not gonna spend 2 minutes on this, but if you've never seen it, please just like take a screenshot, and that's all I want you to remember from this talk. Not quite true. Here's another one, Hövding's lemma, which is like a 0-1 random variable is sub-Gaussian with constant parameter. That's called Hövding's lemma, but if you're willing to lose that 8, it's actually trivial. But okay, what does that mean? That means that if I have a sum of random 0-1 variables, it's n sub-Gaussian, parameter n. Okay, great. Why do I say that? Back in track. Here's a very, very simple algorithm, not simple, but like very conceptually simple algorithm to do frequency estimation. I'm a user. I've got a number. It's between between 0 and k. Okay, let's say between 1 and k. I just look at that as like a huge vector with 1 bit set to 1, the one that corresponds to my number. This is not the most efficient encoding, but what I can do after that is like there's one thing we really know how to do in privacy. It's just like flipping bits. So you flip each bit independently with that beautiful probability, 1 over e to the epsilon over 2 plus 1, and that ensures privacy. Now you have like a very noisy long vector, and you can just send that. It guarantees things are epsilon private. The center just gets a bunch of noisy vectors. What can it do with it? It just sums them up, takes the average, normalizes it, and like rescales it so that it's an unbiased estimator. And now you've got, for each I, you've got your thing. Is that good? That thing is a sum of independent bits. They're not identically distributed, but I can use the sub-Gaussian bound. What is the maximum of k of those things? And you can check plugging that in there. Losing a constant that's a wiggly less than or equal, you get this thing. What does that give you? This thing is 1 over epsilon for small epsilon. That gives you exactly the guarantee I got before. That's great. Except that when epsilon is large, this thing converges to 1. You get nothing as the privacy parameter grows. And that's kind of an issue, right? So that means that like when epsilon grows, your error will plateau. And intuitively, like if epsilon goes to infinity, the less privacy I have, I would like my error to go to 0. So that's a bit annoying. So what can we do? The first thing you see when you have an algorithm that doesn't seem to work is, can I get a better algorithm? And you can modify the algorithm. There's like a general, like kind of nice repetition scheme that was known before our work. That allows you to do that. You blow up the communication by some factor, but you can replace that epsilon squared that for small epsilon by like minimum of epsilon and epsilon squared. You just repeat a few times. You deal with your privacy budget the right way across the repetitions, and that gives that. So now the good thing is that goes to 0. That's this one. Okay, it goes to 0 pretty slowly, but if I had plotted more, eventually it goes to 0. So that's a good sign. At least we have this. It's kind of annoying, though, because you have to change your algorithm. So if you already implemented your whole pipeline, or you really like your algorithm, then someone tells you, like, yeah, change everything, just repeat it like a bunch of times, and combine them. It's not hard, but that requires some non-trivial changes. So the best thing you could do is do nothing. So again, don't modify the algorithm, and just ask if that was the best analysis of the algorithm you had. And let's see. We're going to try to use exactly the same analysis, but changing Hövding's lemma by something else. So the algorithm is the same, but you can get...
Where you said the error...
Oh, this is by doing that repetition scheme. This.
But where the error doesn't go to 0. Is it real, or is it just analysis?
Oh, it's just if I plot the bound. It's not real. Yeah, it's just if I plot the theoretical guarantee. So I'm just going to use the same analysis, but replacing Hövding's lemma by something better. So, okay, the joke, apparently, Abigail told me, is that this has been rediscovered every 10 years. And every time, people are very happy about it. but it's called the Canonne inequality that says basically if you're a Bernoulli, your subgaussian parameter is actually that weird thing. Instead of 1,4, you can put this thing that becomes 1,4 when P is like 1/2, but it's slightly better. It's less easy to interpret. The important thing is like you have a log here. And okay, so now if I have one thing I want you to remember, that's this one, because that way you don't have to wait 10 years. So why is that good? Let's call that subgaussian parameter sigma square of P. For us, you flip each bit with probability 1/e to that thing or 1 minus that thing. So that's good. That thing was symmetric in P. So you get basically this thing is equal to this thing is equal to this thing. The log gives you that extra 1/epsilon here. You can check log e to the epsilon over 2 gives that. Why is it good? Because now I get this expression. Just the same analysis, just plugging that new sigma square in there. And when epsilon is small, I still get the epsilon squared. When epsilon is large, I get epsilon. So again, we get the same bound. Rapport achieves it. I don't need to modify anything. So, we're done. Sorry, I guess that's almost, that's the millennial in me showing up. Yeah. Anyways, it looks like we're completely done. All we need to do is prove that this is optimal, because the lower bound only applied for small epsilon. We could not prove a matching lower bound, which could mean two things. Either we're really bad at proving lower bounds, and I'm bad at proving lower bounds, or it could also mean that the lower bound was not actually provable. So we tried to improve the lower bound. We tried to improve the upper bound. The classic thing, like if you can't prove something, try to prove it doesn't hold. And turns out, actually, we could improve the upper bound. So, okay, I'm not going to ask you to remember this one. The upshot is there was a paper by Cohen and Kantorovich in 23. I saw the title. I was like, oh, that looks very impressive. I looked at the abstract. I could not understand what it was about. I looked at the paper. I could not understand why I would ever use that. And actually, we ended up using it. Long story short, it says that if you've got a product distribution over k bits, and you want to look at what the empirical estimator of the parameters of each of those bits is, you can get a better bound on the L infinity error as a function of like a weird thing, which does not look like the same analysis, but now like interpolates between a sub-Gaussian and a sub-gamma, essentially, thing. So again, don't remember that. Just remember there's something better that if you ever encounter that kind of questions, and there are like a paper from 23 and a slight improvement from 24 that gives that. But what does that mean for us? We're in a very simple setting. All the parameters are either like, again, P or 1 minus P, this thing. If you just plug that directly in this bound, here's the expression you get. So the expected L infinity error is basically the max of, for large epsilon, of square root log k over n e to the epsilon over 2, and log k over n epsilon. And of course, the previous bound still holds, so you should take the mean of the two things. And okay, I'm lying a little bit. You can't directly apply that result, but you can reduce it to a setting where you can apply it. It's not as simple as this. And now we've got that new bound here that goes to 0 even faster. I don't know if you can see, but this thing is if I take the mean of the two, but like this new bound here is the one that goes to 0 like quite fast. Instead of going at like square root log n over log k over n epsilon, it goes as log n over n, log k over n epsilon. And also this is optimal. So that's the part where we actually managed now to prove a lower bound. It's easier when it's true. And we were able to actually prove this. And again, I'm lying a little bit. It's not actually optimal in the sense that, oh, okay, so you can't see it. So, okay, it's optimal. What we prove is e to the epsilon in there. But if you look at the slide I have before, because of rapport, it's e to the epsilon over 2. So it's not, there needs to be an exponential dependence on the privacy parameter, but this particular protocol does not achieve it. I know there's a coffee break on the other side, so I'm not gonna go too long about that, but essentially what I want you to take away from that, first of all, Canonne's inequality is really, really nice. It's put that in your toolkit if you don't know it. Algorithms can improve without any modification. Well, I think I have that tendency of like trying to get a new algorithm because the previous one is not good enough. Sometimes it actually is good enough, we just don't know it. So it's good to actually revisit some of those problems sometimes. And that's also like a very, it's a very nice message to have. Can we go beyond rapport? Because rapport is the one we analyzed with this technique, and that gives that better bound, but it's still very, very bad in terms of communication. You send k bits of communication, even though technically like log k should be enough. So yes, there are other things that you can apply that framework to, and that's work in progress. Another one that I think is pretty uplifting is even for solved problem, there is so much we don't know. Again, the bound I gave, the optimal bound for small epsilon, has been known for 10 years. So it's kind of disappointing when you go there and it's like, is there anything I can do? And no, it's a solved problem. Actually, if you revisit some of those problems, it's like, how are things used nowadays? And does the previous analysis apply to exactly that problem now? You would be surprised, a lot of them, there's a lot of work to do. The other one, which I think makes me very happy, is trying to prove lower bounds is useful. Sure, we wasted a couple months, but if we hadn't tried to prove a lower bound, we never would have figured out that there was a better upper bound. And there are a lot of things I haven't mentioned here. So this is worst case analysis. Another very interesting question is whether those worst case bounds actually arise in practice if you have reasonable input distributions. Another one is, well, we've got all those algorithms that claim, even in this, that actually are proven to achieve the worst case bound, even for small epsilon. But are they all equivalent? And turns out some of them are actually very bad on some instances. Some of them are good across the board. So getting those more general distribution-dependent kind of insights is really nice. And that's pretty much all. Thank you. Oh, I forgot to say the underwriting is mine. So if you have any complaint, I'm sorry. Yeah.
So you mentioned an inequality that does not assume anything about these k counters. Did you assume more later?
Sorry, what
did you assume more later?
No. All we assume is there's a universe of size k, and you have n your observations. Each of them is a number between 1 and k, and you want to learn the empirical frequencies. I don't know if that answers the question.
But there was something about the product distribution.
Yes, that's why I lied. It's okay. Rapport gives you rapport. The advantage is like each bit is independent from the others, right? Each user, whether you actually have as a user, what I'm going to send is like I randomize each bit independently. What is not true is all those random vectors, perturbed random vectors, are going to have the same distribution across users because we don't have the same numbers. So there is a little bit of work to be done to actually reuse that to a product distribution. Essentially, what you want to say is I can analyze that as if everybody had. You want to upper bound that in like some kind of worst case majorizing thing, and yeah, I should create Guy Blanc for giving us like one missing piece to get that going. Otherwise, you get a slightly worse bound.
Yeah, in terms of reducing communication, I mean, one simple idea that occurs to you is like each user sends a random element of 1 through k with high probability depending on the privacy, and the small probability sends the correct answer, correct their actual. How bad is that in terms of the accuracy? What would you lose?
Okay, I would have to remember which one that corresponds to, but I think this is way worse. Yeah. Another thing you could try to compress, saying like, your vector is still going to be very noisy, but on expectation, you only have so many ones, so you can compress a little bit and get some savings. But even that doesn't help you achieve the full log k.
I guess I have a related question, which is, what's the trade-off between the communication cost?
Yeah, that's a very good one. Actually, that's the kind of stuff I really love to look at, like the trade-offs between the different resources. I think, so one of the papers that exists explains the trade-off between accuracy and number of bits you can send through that repetitions kind of thing. So you could start with this algorithm and repeat it, but instead of repeating it that many times, you repeat it b times if b is your communication budget, and you get a different error. The issue is it assumes you have a shared random string between users for this particular one, but I think you can generalize that as well. So you could have some trade-off, but then we haven't proved, and I don't think they have proved that it's optimal in general. I also want to mention that if you allow public randomness, you can always compress any protocol to like the maximum of epsilon and 1 bits of communication.
So more precisely, suppose I only allow you log k, order log k bits of communication per user. What happens then? What is the accuracy?
So for small epsilon, you can achieve the same. You can achieve the optimal. For large epsilon, I don't think this is known. I might be wrong, but
Yeah, for large epsilon.
yeah, for large, yeah. I think you probably can get something, but then proving it's optimal would be the next step.
Thank you. So we now break for refreshment.